Hello, everyone. My name is Nikita. I am a PhD student at Humboldt University of Berlin and research associate at Pareto. And today I'm going to talk about feature selection in credit scoring and multi-objective particle form optimization technique that we developed. I'm going to start with some background. What is credit scoring and why is feature selection important there? Then I'm going to talk about the proposed multi-objective framework and then move on to the experimental design and some preliminary empirical results that we gathered on credit scoring datasets. So let's start with some background. Credit scoring refers to the use of statistical models to support loan approval decisions. A customer comes in asking for a loan, and a financial institution needs to make a decision whether to approve the application and issue the loan or reject it. Fintech companies heavily rely on automation of such processes, and to do that, they need to build good models that predict the probability of default. And to build good models, you also need good data. Some data can be extracted from the application form that a customer fills out when applying for a loan. Other data is usually purchased from different third-party providers, like credit bureau scores, banks, and other institutions. For instance, companies can buy data on the previous loans a customer might have with different banks, or geographical data that refers to the neighborhood their customer is registered. There are many other sources not listed on the slide, like data from telecommunication providers or data from smartphone usage. The volume of data and the number of potential data sources emphasize the importance of feature selection in credit scoring. It becomes very important to distinguish noisy and redundant information from the information that contains signal on the credit reliability of a customer. Traditionally, feature selection is considered as a single objective task with the goal of improving performance of the scoring model. However, in credit scoring, there are multiple goals that could be considered as objectives within feature selection. First of all, financial institutions are interested in improving performance of the scoring models because the accuracy of the scorecard affects its profitability. The performance is usually measured in terms of AUC indicator, which reflects the accuracy of ranking of the loan applicant. Another dimension is comprehensibility. Some companies and banks have to follow strict regulations that enforce using comprehensible scoring models. Model explainability is also important for customers who want to know exactly the reasons why the decision was made that way. Having less features improves both comprehensibility and explainability of the model. A slightly different dimension is data acquisition costs. In practice, features are usually purchased in groups and not on an individual basis. For instance, if a financial company signs a contract with credit bureau, they provide information about the applicant. It could be that you can extract multiple features from that information, but it is not the case that each individual feature needs to be paid for, given that the information about the applicant is already provided. Plus, different providers have different payment options. This decorrelates the number of features and the cost of features. And together, this contributes three different objectives that are important to be optimized during the feature selection. Research has come up with different techniques that enable multi-objective feature selection. The simplest solution is to aggregate multiple objectives into a single one, for instance, weighting them with equal weights. Another approach is to introduce a budget constraint. The disadvantages of these two approaches is that you need to specify weights of the objectives or the budget constraint beforehand. When you don't know these values, you need a truly multi-objective method that optimizes distinct objectives simultaneously. This is achieved by methods that produce not a single output, but a Pareto frontier. The Pareto frontier is a set of non-dominated solutions where you cannot improve on one of the objectives without hurting one of the others. This Pareto frontier can be used by a decision maker to represent a set of possible solutions, and depending on the trade-off between different objectives and the context of a specific decision, a manager can decide which solution is more preferable. Previous research has developed multiple methods and algorithms that can solve this task and output the set of non-dominated solutions. Most of the multi-objective optimization techniques are inspired by evolutionary algorithms that take their root in different natural processes. NSGA2, which stands for the non-dominated sorting-based genetic algorithm, is one of the most well-known multi-objective optimization algorithms. Recently, NSGA3 was proposed as an improvement of NSGA2 that handles issues appearing beneath many objective optimization. Research in different fields outside of the feature selection domain have also shown that particle swarm optimization techniques outperform genetic algorithms across a wide range of different optimization tasks. However, looking at the credit scoring domain, the research on multi-objective feature selection has been scarce. Maldonado and colleagues developed a feature selection method embedded in the support vector machine. It allows optimizing performance of the model and cost of the features, but the disadvantage of this method is that it can only be used with support vector machines. Another study has used NSGA2 to perform multi-objective feature selection. They only used the number of features and the model performance as two objectives. We argue that only considering the number of features as a proxy for model comprehensibility ignores the important dimension of data acquisition costs. This is why we develop a feature selection framework that optimizes three distinct objectives: performance of the scorecard, measured with the area under the ROG curve; number of selected features, which stands as a proxy for model comprehensibility; and data acquisition costs, which is another important dimension relevant to financial institutions. Based on the previous research results, we also adapt a particle swarm optimization algorithm to improve feature search compared to genetic algorithms that are frequently used in feature selection applications. We denote our algorithm as AgMOPSO, archive-guided multi-objective particle swarm optimization. Let me show how it works. It initializes with a swarm of random particles, where each particle is just a binary coded vector, where 0 stands for not including this feature into the model and 1 stands for including this feature. Based on each of the particles, we can train a model using these corresponding features and evaluate its fitness in terms of AUC, number, and cost of features. The evaluated particles are placed into the archive, which is constantly updated within the algorithm with the best solutions. The algorithm then iteratively produces new generations of particles that try to improve on the performance of previous best solutions. The swarm is guided towards new areas of the search space using two different search regimes. The first one is called immune-based search. Immune-based search is inspired by genetic algorithms using such operators as mutation and crossover. The new set of particles produced as a result of the immune-based search is again evaluated using a model trained on the features based on the particle values, and the best solutions produced within this search are placed in the archive. The second search regime is called the PSO-based search. The idea behind this search is to move particles in the multidimensional objective space towards the swarm leaders. The swarm leaders are the particles which have the best performance in terms each of the three objectives. By changing the particle values such that they become closer to the swarm leaders, the swarm moves towards this direction and identifies solutions that can perform better. As a result of this search, we again arrive at a new set of particles that is evaluated in terms of their fitness, and the archive is updated to incorporate the best solutions. So let's test performance of our algorithm on some real data. For these purposes, we gathered a library of 9 publicly available credit scoring datasets. As you can see in this table, the number of features and sample size varies a lot from one dataset to another, which allows us to test our framework in a number of different environments. On each dataset, we use the same modeling pipeline to perform experiments. First, since information about data acquisition costs is not available on all datasets, we simulate acquisition costs. For each continuous feature, we draw cost from a uniform distribution. For each categorical feature, we do the same and implement the group-based cost for dummy features coming from a given categorical attribute. This simulates the group-based purchasing of features that is frequent in the practice. For instance, the categorical feature employment type is encoded as a set of dummies, and the cost for this feature is only charged once if at least one dummy is present in the selected features. Next, we perform data partitioning. On 70% of our data, we run 5-fold cross-validation to perform feature selection. Another 30% serve as a holdout sample to evaluate performance of feature selection methods. Regarding the benchmarks, apart from AgMOPSO, we are using NSGA2 and NSGA3, which are two popular multi-objective optimization algorithms. All three multi-objective algorithms use the same set of objectives: AUC, number of features, and their acquisition cost. Finally, we also use a naive benchmark, a full model with all features that performs no feature selection. To ensure robustness of our results, we run the modeling pipeline displayed on this slide 20 times on each of the datasets and aggregate performance across the trials. This table compares results of the three multi-objective algorithms. The values in the table refer to mean ranks across 9 datasets times 20 modeling trials. Lower values means better performance. We measure performance in terms of 5 statistical metrics that are popular in multi-criteria optimization. I will not go into much detail describing each of these metrics. As you can see on the slide, they refer to different aspects of the outputted Pareto frontiers, like cardinality or diversity. As you can see from the table, AgMOPSO performs best in 3 indicators: hypervolume, which reflects the area covered by the Pareto frontier; cardinality, which refers to the number of solutions on the frontier; and convergence, which indicates the degree to which the Pareto frontier approximates the theoretical true frontier. As you can also see, NSGA2 and 3 perform better in terms of diversity. Arguably, diversity is not that important in the feature selection application compared to other indicators. We are mostly interested in the area of the search space with a high AUC and small number and cost of features. Now, let's take a look at the best individual solutions produced by multi-objective algorithms and also compare them to the full model with no feature selection. The last 3 columns of the table represent mean ranks in terms of AUC, number of features, and data acquisition cost. First, we see that all multi-objective algorithms perform better than the full model. Second, we can see that AgMOPSO achieves the best AUC across the algorithms. At the same time, we see that NSGA3 achieves a lower number of features and acquisition cost. It is important to note that this comes at a cost of having a much lower AUC. This indicates that compared to the genetic algorithms, AgMOPSO more efficiently explores the search space with a higher AUC. This is also corroborated by the example Pareto frontier from one of the datasets. Here, AgMOPSO solutions are represented with red dots, whereas blue and green colors refer to the solutions of NSGA2 and 3. As you can see here, AgMOPSO identifies more non-dominated solutions compared to the benchmarks. Moreover, you can also see that AgMOPSO has more solutions in the high AUC search space. This allows us to conclude that AgMOPSO performs highly competitive compared to other benchmarks and more efficiently explores the relevant search regions. All right, this is the end of my talk. To sum up, we discussed the importance of feature selection in high-dimensional environments that are typical for credit scoring and conflicting goals of this business context. We suggested a new feature selection framework that optimizes 3 distinct objectives: AUC, which stands for performance of the scoring model; number of features, which serves as a proxy for model comprehensibility; and data acquisition cost. We also used a novel PSO algorithm to improve feature search. We performed experiments on 9 credit scoring datasets and showed that AgMOPSO outperforms benchmarks in terms of hypervolume, convergence, and cardinality of the Pareto frontier. We also demonstrated that it more efficiently explores search space with higher AUC compared to the benchmarks and significantly reduces number of features and data acquisition costs compared to the full model with no feature selection. Thank you very much for your attention, and I would be happy to answer any questions you might have.